The air touching your skin right now has been on a journey you wouldn't believe. It crossed entire oceans, swept over mountain ranges that pierce the clouds, drifted through valleys where no human has ever walked. Some of the oxygen molecules you're breathing in at this very moment were once part of a rainstorm over the Amazon, or a snowflake that landed on the peaks of the Himalayas, or the morning mist rising from a lake in Scandinavia. The air doesn't belong to any one place. It moves endlessly, carrying with it the memory of everywhere it's been. And tonight, we're going to follow that journey. We're going to drift through the atmosphere the way the wind drifts, without force, without hurry, just allowing ourselves to be carried along. Because weather isn't just something that happens outside your window. It's the most ancient story on Earth, and it's being written right now, all around you. Even in the stillness of this moment, you might not feel it, but the air in your room is moving. Very slowly, almost imperceptibly, it's circulating. Warm air rises, cool air sinks. There are invisible currents flowing around your body, responding to your warmth, to the temperature of the walls, to the faint breath you exhale. This same principle, this same dance of warm and cool, is what creates every gust of wind, every storm, every gentle breeze that's ever moved across the surface of our planet. And as we move through tonight together, you're going to discover things about weather that will change the way you see the world. Not in a dramatic way, but in a quiet way. The kind of way that settles into your understanding and makes everything feel a little more connected, a little more intentional, a little more peaceful before this night ends. You'll understand why the calmest place in a hurricane is also the most dangerous, and why that paradox teaches us something profound about finding peace in chaos. We'll discover what makes the sky turn green before a storm, and why that eerie color has captivated humans for thousands of years, showing up in ancient myths and modern photographs alike. And you'll learn about whether that happens not on Earth, but in the space between here and the stars, where solar winds carry particles across millions of miles to paint our skies with light. But we're not rushing toward any of these revelations. We're going to take our time. As we drift deeper into this journey, the pace will soften naturally, the way twilight softens into night, the way conversation slows down when you're talking with someone you trust and there's nowhere else you need to be. There's something you should know about clouds before we go any further. When you look up at a cloud, drifting peacefully across a blue sky, it looks weightless, doesn't it? Like a wisp of nothing, like cotton candy or steam. But here's the thing that most people never realize. Clouds are heavy, incredibly heavy. A single cumulus cloud, one of those puffy, white, friendly-looking clouds you might see on a pleasant afternoon, weighs about the same as 80 elephants. Yes, 80 elephants floating above your head. The water droplets and ice crystals that make up that cloud, if you could gather them all together, would weigh around 500,000 pounds. And yet it floats. It doesn't fall. And the reason it doesn't fall is because those water droplets are so tiny, so unbelievably small, that the upward push of warm air rising beneath the cloud is stronger than gravity pulling down on those droplets. Each droplet is only about 20 micrometers across, which is smaller than the width of a human hair. They're so light individually that they drift in the air the way dust drifts in a sunbeam. So when you see a cloud, you're really seeing billions upon billions of these tiny droplets, all suspended together, collectively holding the weight of 80 elephants in the sky. And speaking of things we get wrong about water in the sky, let's talk about raindrops. If you were asked to draw a raindrop right now, you'd probably draw a teardrop shape, wouldn't you? pointed at the bottom, rounded at the top. That's how raindrops are drawn in every cartoon, every weather icon, every illustration. But real raindrops don't look like that at all. When a raindrop falls through the air, it's not teardrop shaped. It's actually more like a hamburger bun, rounded on top and flat on the bottom. The air pressure pushing up on the bottom of the falling drop flattens it out, while the top stays nicely rounded. Small raindrops are almost perfectly spherical, like tiny ball bearings. Larger raindrops get that hamburger bun shape, and really large raindrops, the ones that form in heavy storms, get so big and so flattened that they become unstable. They wobble and distort and eventually break apart into smaller drops. There's actually a maximum size a raindrop can be before it splits, and that's about 5 millimeters across. Any bigger than that, and the raindrop can't hold itself together as it falls. It's a small detail, the true shape of a raindrop, but once you know it, you can't unknow it. And there's something peaceful about understanding these tiny truths about the world around us. Here's another one of those peaceful truths. The reason you see lightning before you hear thunder. You probably already know this on some level, but let's really think about it for a moment. Light travels at about 186,000 miles per second. That's so fast it's almost instantaneous for any distance we experience in our daily lives. Sound, on the other hand, travels at about 767 miles per hour, or roughly 1,000 feet per second. That's fast in human terms, but compared to light, it's almost standing still. So when lightning strikes, the light from that flash reaches your eyes almost immediately. But the sound of the thunder has to physically travel through the air to reach your ears. Air molecules have to bump into other air molecules, passing the vibration along like a wave moving through water. And that takes time. For every 5 seconds between the flash and the thunder, the lightning is about 1 mile away. You can count it yourself during a storm. See the flash, start counting. 1 Mississippi, 2 Mississippi, 3 Mississippi. If you hear the thunder after 3 seconds, the lightning was about 3/5 of a mile away. It's a simple calculation, but it connects you to the storm in a tangible way. It tells you exactly where you stand in relation to that enormous release of energy. Let that settle for a moment. The thing about weather is that it's always doing something, even when it seems like nothing is happening. On a perfectly calm day, when there's not a breath of wind and the sky is clear and blue, the atmosphere is still in motion. Air is still rising and falling. Water is still evaporating from the oceans, rising up into the atmosphere, condensing into invisible vapor. Temperature gradients are still forming. Pressure systems are still shifting. A perfectly calm day is really just weather in balance. All the forces pushing and pulling with equal strength, so that from where you're standing, everything seems still. But zoom out, look at the whole planet, and you'd see that the atmosphere is never at rest. It's always flowing, always seeking equilibrium, always responding to the sun's warmth and the Earth's rotation and the presence of mountains and oceans and ice and forests. Weather is the planet breathing. You might notice your breathing has already slowed slightly since we started. That's natural. Let it. There's a rhythm to breath that mirrors the rhythm of weather. The way pressure builds and releases, the way air moves in and then out. You don't have to think about it. Your body knows what to do. And in the same way, you don't have to work at following this journey. There's nothing you need to do but listen. Or not listen, really. Either way, the weather continues. The air keeps moving. The clouds keep forming and dissolving. the water keeps cycling from ocean to sky to rain to river to ocean again. It's been doing this for 4 billion years, since Earth first had an atmosphere. And it'll keep doing it long after we're gone. There's something deeply comforting in that continuity, in knowing that these processes are so much larger and older than any single moment of worry or stress or sleeplessness. So tonight, we're going to let the weather carry us. We're going to explore the atmosphere the way you might explore a forest, noticing the details, understanding the patterns, but mostly just being present with it. We'll talk about winds that circle the entire globe, about the invisible boundaries where different air masses meet, about the strange and beautiful things that happen when water changes from liquid to vapor to ice and back again. We'll discover why sailors once feared certain latitudes, why deserts exist where they do, and what a snowflake can teach us about the nature of uniqueness. But we're in no rush. Let the pace of this journey slow down naturally, the way your thoughts slow down as night deepens, the way the world outside your window has already settled into its own quiet rhythm. The weather is patient. It takes its time. A cloud might take 20 minutes to form, an hour to cross the sky, and then it dissolves, returning to invisible vapor as if it was never there at all. But it was there. You saw it, and in seeing it, in noticing it, you were part of its story, just as it was part of yours. That's what we're doing here. We're noticing. We're letting ourselves be part of the larger story that's always happening, always unfolding, in the air all around us. And as we move forward together, deeper into the night and deeper into understanding, remember that there's nowhere you need to be but here. The weather outside continues whether you're paying attention or not. The wind blows. The temperature shifts. The humidity rises or falls. And inside, where you are now, you can simply rest in knowing that all of this is happening. That you're held within this vast system of air and water and energy, and that for these moments, all you need to do is drift along with it. Lightning is one of those phenomena that seems almost impossible when you really think about it. The air around us right now, the air you're breathing, is an insulator. It doesn't conduct electricity under normal circumstances, and yet, during a storm, the sky itself becomes a conductor, and electricity flows through it in brilliant, branching streams of light. To make that happen, to force electricity through air, requires an enormous amount of voltage. We're talking about somewhere between 100 million and 1 billion volts. That's not a typo. 1 billion volts building up between the ground and the clouds, or between different regions within a single cloud, until the electrical resistance of the air breaks down completely and current can flow. When that happens, when lightning flashes, the channel of air through which the electricity moves heats up almost instantaneously. And when I say heats up, I mean to temperatures around 30,000 Kelvin, which is roughly 5 times hotter than the surface of our sun. That narrow channel of superheated air, maybe an inch or two wide, reaches these extraordinary temperatures in less than a millisecond. Now, when air heats up that quickly, it expands violently. The air molecules in that channel suddenly have so much thermal energy that they need more space, and they push outward in all directions at once. This creates a shock wave, a sudden compression of the surrounding air, and that shock wave is what we hear as thunder. It starts as a sharp crack where the lightning is closest, but as the sound wave travels outward and bounces off clouds and hills and buildings, it rumbles and rolls. The reason thunder sometimes seems to last for several seconds is because you're hearing the sound from different parts of the lightning bolt reaching you at slightly different times. Lightning isn't a single straight line, after all. It branches and forks and zigzags, and each section of that path is creating its own sound. They all blend together into that characteristic rolling boom. You've probably counted seconds between lightning and thunder to estimate distance. That childhood game is actually solid science. Sound travels at a fairly consistent speed through air at sea level. So counting the seconds and dividing by 5 gives you a pretty accurate measure in miles. It's one of those simple calculations that connects you directly to the physics of the moment. Most of the lightning we see is cloud to ground, the kind that reaches down from the storm and touches the earth. But that's actually the least common type. The majority of lightning happens entirely within clouds or between clouds, and we never see it directly. We just see the clouds light up from the inside, glowing briefly as electricity arcs from one region to another. This is sometimes called sheet lightning, and it can make the entire horizon flicker like a distant strobe. Then there's cloud-to-cloud lightning, which jumps from one storm cell to another. And sometimes you can see these as bright flashes that seem to connect separate thunder. There's also something called heat lightning, which isn't actually a different type of lightning at all. It's just regular lightning from a storm that's so far away you can't hear the thunder. You see the flashes on the horizon on a summer night, lighting up distant clouds, but there's no sound. It's called heat lightning because it tends to happen on hot, humid nights when storms are brewing far away, but it's the same electrical discharge as any other lightning. The silence makes it feel almost peaceful, like the storm is happening in another world. And here's something most people never know. Lightning isn't confined to the lower atmosphere where storms happen. Above the clouds, in the thin air where planes fly, other forms of lightning paint the darkness. They have names like sprites and jets and elves, and they reach upward from the tops of thunderstorms toward space. We'll rise to that height later, when we drift into the upper atmosphere and explore the strange and beautiful phenomena that happen in the twilight zone between weather and space. But for now, let's stay here, closer to the ground, where storms gather their power and the air itself becomes electric. Storm systems are remarkable pieces of atmospheric machinery. They don't just happen randomly. They form according to specific conditions, and they organize themselves in ways that seem almost intentional. It starts with warm, moist air. This air is lighter than the cooler, drier air around it, so it wants to rise. As it rises, it cools, and as it cools, the moisture in it begins to condense into water droplets. This releases heat, latent heat, which was stored in the water vapor. That release of heat warms the rising air even more, making it more buoyant, causing it to rise faster. It's a feedback loop. The warmer the air, the higher it rises. The higher it rises, the more moisture condenses. The more moisture condenses, the more heat is released. And so the storm builds, feeding on itself, growing taller and more powerful. An ordinary thunderstorm might reach heights of 30 or 40,000 feet. The clouds tower like mountains in the sky, their tops flattening out when they hit the tropopause, the boundary between the troposphere, where weather happens, and the stratosphere above. That flattening creates the distinctive anvil shape you see on mature thunderstorms. But some storms go beyond this. Some storms organize into structures called supercells, and these are among the most powerful and longest-lasting storm systems on Earth. A supercell isn't just a tall cloud. It's a rotating column of air, sometimes 10 miles across. with winds inside it that can exceed 150 miles per hour. The rotation comes from wind shear, from differences in wind speed and direction at different altitudes. As the storm grows, it begins to tilt, and that tilt allows the updraft and downdraft to coexist without interfering with each other. The updraft keeps feeding the storm with warm, moist air, while the downdraft brings rain and cool air down. This balance can allow a supercell to last for hours, traveling hundreds of miles, spawning lightning and hail and sometimes tornadoes. Tornadoes form when that rotation tightens and extends down from the cloud base toward the ground. Not every supercell produces a tornado, but when conditions are right, when the wind shear is strong enough and the instability is high enough, a funnel can descend. It starts as a rotating column of air that's invisible at first. Only when it picks up dust and debris, or when the pressure drops enough for water vapor to condense, does it become visible. The classic funnel shape is narrower at the bottom and wider at the top, connected to the rotating cloud base above. Wind speeds inside a tornado can exceed 200 miles per hour, sometimes even 300 in the strongest ones. The damage isn't just from wind, though. It's from the objects the wind picks up and hurls like missiles. Tornadoes are localized, usually less than a mile wide, and they typically last only a few minutes. But in those minutes, they can completely alter the landscape. Now, remember earlier when I mentioned that the sky sometimes turns green before a storm? This is the moment to understand why that happens. It's not every storm, and it's not in every part of the world. But under certain conditions, the sky takes on an eerie greenish hue, and when people see it, they know instinctively that something significant is coming. The green comes from light scattering. Specifically, it happens when a storm contains a lot of hail, and the setting or rising sun is at just the right angle. Sunlight at those times of day is already reddish because it's traveling through more of the atmosphere. When that reddish light passes through the blue and white ice particles in the hail-laden clouds, the combination produces a green tint. It's the same principle as mixing yellow and blue paint to get green, except it's happening with light. The thicker the hail, the more pronounced the green. So when you see a green sky, you're seeing evidence of powerful updrafts strong enough to suspend large chunks of ice high in the cloud. That's why it's associated with severe weather. It's a visual signal that the storm has real energy, real structure, real potential for intensity. Standing under a supercell, you'd feel the temperature drop suddenly. It can fall 10 or 15 degrees in just a few minutes as the draft brings cooler air from higher altitudes down to the surface. The air would smell sharp, electric, full of ozone from the lightning. Your hair might stand on end if you're close to where a strike is about to occur. And that's not just an expression. It's a real physical effect from the buildup of electrical charge. The wind would shift, first coming from one direction, then suddenly changing as the storm's circulation takes over. Everything would feel charged, expectant, as if the atmosphere itself is holding its breath before releasing all that pent-up energy. Let's take a moment here and just pause. 5 seconds of quiet to let all of that settle. To imagine what it's like to stand in that space between calm and storm. To feel the air change around you. To know that something immense is about to happen. Now, let's talk about what falls from these storms. Rain, obviously, but rain is just the beginning. Water in the atmosphere takes many forms, and each one tells a story about the conditions that created it. Snow is perhaps the most beautiful and most complex. Snowflakes form when water vapor in a cloud freezes directly into ice crystals. This doesn't happen around dust or pollen or any other microscopic particle. A tiny nucleus that gives the ice something to form around. Once the crystal begins to grow, it develops into a hexagonal structure because of the way water molecules bond together when they freeze. The angle between hydrogen and oxygen in a water molecule naturally creates a six-sided symmetry. So every snowflake, no matter where it forms, has 6 sides or 6 points. As the crystal falls through the cloud, it encounters different temperatures and different levels of humidity, and these conditions affect how it grows. If it passes through a region with lots of moisture, the arms of the crystal grow longer. If it passes through a drier region, the growth slows. If it tumbles through warmer air, the edges might melt slightly and then refreeze. The path each snowflake takes through the cloud is unique. And because that path determines how the crystal grows, each snowflake ends up with a unique shape. That's why people say no to snowflakes or identical. It's not an absolute statement, mathematically speaking. In theory, 2 snowflakes could take identical paths and end up identical. But the probability is so astronomically low that in practice, it never happens. Each snowflake is a tiny, frozen record of its journey through the cloud. The geometry of snowflakes has fascinated people for centuries. There are dozens of different types, categorized by their structure. Stellar dendrites, with their intricate branching arms. Simple hexagonal plates, columns, needles, capped columns. Some snowflakes are simple and others are astonishingly complex, with layers of detail that you can only see under magnification. And yet all of them, every single one, follows that 6-fold symmetry. It's one of nature's most elegant examples of mathematical order, emerging from physical laws. Hail is a different story entirely. Hail forms when a raindrop or ice crystal gets caught in the powerful updraft of a storm and is carried up into the freezing part of the cloud. It accumulates layers of ice as it rises and falls and rises again, sometimes cycling through the storm multiple times before finally becoming heavy enough that even the updraft can't hold it. If you cut a hailstone in half, you'd see those layers, like rings in a tree, each one representing a trip through a different part of the storm. Large hailstones, the ones that cause damage, require exceptionally strong updrafts. A hailstone the size of a golf ball needs winds of at least 60 miles per hour to stay aloft. Larger ones, the size of baseballs or softballs, need even stronger winds. When a storm produces giant hail, you know the updraft inside it is extraordinary. A vertical wind tunnel capable of suspending pounds of ice thousands of feet in the air. And then there's the smell of rain. You know that smell, the one that rises from the earth when the first drops fall after a dry spell. It has a name, petrichor. It comes from oils that plants release during dry periods, oils that accumulate in soil and on rocks. When rain strikes the ground, it doesn't just wet the surface. The impact creates tiny air bubbles that burst and release aerosols, microscopic droplets that carry those oils into the air. You're breathing in the patience of plants, the chemical signals they created during days or weeks of waiting for water. There's also a compound called geosmin, produced by soil bacteria, that contributes to that earthy scent. Humans are incredibly sensitive to geosmin. We can detect it at concentrations as low as 5 parts per trillion. That's less than a single drop in an Olympic swimming pool. It's thought that this sensitivity evolved because moist soil and water sources were crucial for survival. So our ancestors, who could smell rain coming, had an advantage. The scent of rain, then, is woven into our biology. It's connected to something ancient in us, something that recognizes rain as light, as essential. Let's shift now to the way light interacts with water and ice in the atmosphere, because this is where weather becomes art. Rainbows are the most familiar example. They form when sunlight passes through raindrops and is refracted, bent as it enters the drop, reflected off the back of the drop, and refracted again as it exits. Different wavelengths of light bend by different amounts, so the white sunlight separates into its component colors: red, orange, yellow, green, blue, indigo, violet. Red bends the least, violet bends the most. The rainbow you see is actually a full circle, but you usually only see an arc because the ground blocks the lower half. If you were in an airplane or on a mountain looking down at rain in a valley, you could see the full circle. The position of the rainbow depends on your position relative to the sun and the rain. The sun has to be behind you, the rain in front of you, and the angle has to be just right, about 42 degrees between the incoming sunlight, the raindrop, and your eye. That's why everyone sees their own rainbow. The rainbow you see is created by light passing through drops that are in a specific position relative to you. Someone standing next to you is seeing light from different drops. It's personal in a strange way. Your rainbow exists only for you. On cold days, when the air is filled with ice crystals instead of raindrops, other optical effects appear. Sundogs, for instance, which are bright spots of light that appear on either side of the sun, sometimes showing a bit of color. They form when sunlight passes through flat, hexagonal ice crystals that are floating horizontally in the air. The crystals act like prisms, bending the light and creating those spots of brightness. There are also halos, perfect circles of light around the sun or moon, formed when light passes through ice crystals in high, thin cirrus clouds. These halos have a radius of exactly 22 degrees because of the geometry of the ice crystals. They're common, actually, much more common than rainbows. But most people don't notice them because they're subtle and they require you to look toward the sun, which we're naturally inclined not to do. Picture light bending through millions of ice crystals, each one tumbling slowly through the air, each one turning like a tiny prism. The light that reaches your eye has been through a journey of its own, bouncing and bending and splitting into colors. The sky becomes a canvas where physics paints with light, and you're there to witness it. These moments don't require anything from you except attention. They happen whether you notice or not, but noticing them, really seeing them, adds a layer of wonder to the day. Rainbows happen during the day, when the sun is out and rain is falling. But under specific conditions, the moon can create its own ghostly version. We'll encounter those later, when we drift deeper into this journey and the light grows softer, when we explore the quiet phenomena that happen after dark. For now, just know that they exist, that the moon's light is strong enough, under the right circumstances, to bend through raindrops and create a pale, almost colorless arc. They're rare and they're hauntingly beautiful, and we'll find our way to them when the time is right. Animals know weather in ways we've forgotten, or perhaps never knew. They read the atmosphere with senses we don't possess, detecting changes that are invisible to us. Many birds and insects can sense shifts in barometric pressure, the weight of the air pressing down on the Earth's surface. When a storm approaches, air pressure drops, and animals feel this change. It's not abstract to them. It's as real as the feeling of wind on your face. Some fish swim deeper when pressure drops. Birds fly lower. Even spiders adjust their webs, building them stronger when low pressure suggests rain is coming. These aren't learned behaviors passed down through generations. They're instinctive responses to atmospheric changes that the animal's nervous system can detect directly. The atmosphere is speaking to them constantly, and they're listening in ways we can barely comprehend. Consider the monarch butterfly. This delicate insect, weighing half a gram, with wings so thin you can see through them, makes a migration of 3,000 miles. They travel from Canada and the northern United States all the way to specific groves of trees in the mountains of Mexico. And they do this using cues from the sun, from the Earth's magnetic field, and from the wind. Monarchs born in late summer have never made this journey before. Their parents are dead, their grandparents are dead, and yet they know where to go. They ride thermal currents, columns of rising warm air that form when the sun heats the ground unevenly. A butterfly weighing as much as a few flower petals catches these invisible currents and lets them carry her upward, conserving energy, gliding on nothing but heated air. From our perspective on the ground, we see a butterfly drifting seemingly at random, but she's reading the sky. She knows where the thermals are. She knows when to flap and when to glide. The atmosphere is her highway, and she navigates it with a precision that scientists are still trying to fully understand. Birds do this too, of course, but on an even grander scale. Hawks and eagles spiral upward on thermals, rising hundreds of feet without a single wing beat. They're not just flying, they're reading the sky like a map you and I can't see. They know where the air rises, where it sinks, where the wind is smooth and where it's turbulent. They navigate by warmth, by the subtle differences in air density, by the way sunlight strikes the earth and creates these invisible rivers of rising air. Migrating birds use thermals to travel vast distances. Storks flying from Europe to Africa seek out thermals over land because there are no thermals over the ocean, and without them, the journey would require too much energy. So they take routes that keep them over land as much as possible, funneling through narrow corridors like the Strait of Gibraltar, where thousands upon thousands of birds pass through during migration season, all of them riding the same atmospheric currents. All of them reading the same invisible map. Notice how that image settles in your mind. Birds spiraling upward on columns of warm air. Butterflies drifting on currents we can't feel. The atmosphere as a living thing that other creatures navigate with an ease we can only imagine. That weather has always shaped human history. Though we sometimes forget this. We live in an age of climate control, of buildings that insulate us from the outside world, of technology that lets us predict storms days in advance. But for most of human existence, weather was destiny. A good growing season meant survival. A drought meant famine. Unusual cold meant hardship. Entire civilizations have risen and fallen based on shifts in weather patterns that lasted decades or centuries. The Maya, for instance, built one of the most sophisticated civilizations in the ancient world. They developed advanced mathematics, a complex writing system, and monumental architecture. Their cities held tens of thousands of people. And then, in the 9th and 10th centuries, many of their great cities were abandoned. The population declined dramatically. For a long time, archaeologists debated why. War, disease, social upheaval. But evidence from tree rings, from lake sediments, from cave formations suggests that the primary cause was drought. Not a single bad year, but a series of droughts spanning decades. The Maya depended on seasonal rainfall for their agriculture. When the rains became unreliable, when the dry seasons stretched longer, the agricultural system couldn't support the population. Cities that had thrived for centuries emptied. People dispersed to areas where water was more available. The classic Maya collapse wasn't caused by a single dramatic event. It was weather, slow and relentless, changing the conditions that had allowed their civilization to flourish. Then there's the Little Ice Age, a period of cooling that lasted from roughly the 14th to the 19th century. Temperatures across Europe and North America dropped. Glaciers in the Alps advanced, swallowing villages. Winters became longer and harsher. The Thames River in London froze solid multiple winters in a row, thick enough that people held frost fairs on the ice, with vendors and entertainment and even carriages crossing from one bank to the other. Paintings from that era show people ice skating on canals in the Netherlands that haven't frozen in modern times. Harvests failed more frequently. Growing seasons shortened. The cooling wasn't uniform. It varied from decade to decade and region to region, but it left its mark on history. It influenced migration patterns, economic systems, even the spread of disease. And we know about it because the weather leaves traces. Tree rings are one of those traces. Each year, a tree adds a new ring of growth. In good years, when water is plentiful and temperatures are favorable, the ring is wide. In bad years, when drought or cold limits growth, the ring is narrow. By studying cores taken from old trees, some of them hundreds or even thousands of years old, scientists can reconstruct past climates with remarkable precision. They can see the years of drought that affected the Maya. They can identify the coldest decades of the Little Ice Age. They can track temperature and rainfall, patterns going back centuries. Long before anyone was keeping written weather records, ice cores go even further back. In Antarctica and Greenland, snow falls and compresses into ice, layer upon layer, year after year, building up over millennia. When scientists drill down through this ice, they're drilling through time. Each layer contains air bubbles, tiny pockets of atmosphere trapped when the snow falls. The air inside these bubbles is the same air that existed at that moment in history. When they extract a core from deep in the ice sheet, they're opening time capsules. The air inside is the same air that humans breathed when mammoths still walked across the tundra, when the earth was in the grip of an ice age, when the continents were covered with glaciers. By analyzing the composition of this ancient air, the ratio of different isotopes, the concentration of greenhouse gases, scientists can reconstruct not just temperatures but entire climate systems from tens of thousands of years ago. Weather is memory. It leaves its signature in trees, in ice, in sediment layers at the bottom of lakes. And by reading these signatures, we're able to see that climate is always changing, has always been changing, operating on timescales much longer than a human lifetime. The ocean and the atmosphere are in constant conversation. What happens in one affects the other in ways that ripple across the entire planet. The most well-known example of this is probably El Niño and La Niña, which are opposite phases of a climate pattern that involves sea surface temperatures in the tropical Pacific Ocean. During El Niño, a band of warm water develops across the central and eastern Pacific, and this relatively small change in ocean temperature has massive effects on weather worldwide. It shifts the jet stream, alters rainfall patterns, and affects storm tracks. The western coast of South America, which is usually dry, gets heavy rains. Australia experiences drought. The Atlantic hurricane season becomes less active. All of this from warmer water in one part of one ocean. La Niña is the opposite phase, with cooler than normal water in the same region, and it brings its own set of changes. More Atlantic hurricanes, increased rainfall in Southeast Asia, drier conditions in the southern United States. The atmosphere and ocean are coupled systems. Warm water puts more moisture into the air, which changes atmospheric circulation, which in turn affects ocean currents. It's a feedback loop, complex and interconnected, and shifts in one place propagate through the system, creating effects thousands of miles away. The Gulf Stream is another example of this connection. This powerful ocean current carries warm water from the Gulf of Mexico, up along the eastern coast of North America and then across the Atlantic toward Europe. It releases enormous amounts of heat into the atmosphere as it flows. This heat warms the air over Europe, making places like Ireland and England much milder than other locations at the same latitude. Without the Gulf Stream, London would have winters like Labrador. The ocean is essentially acting as a heat transport system, moving thermal energy from the tropics toward the poles, and the atmosphere responds to this movement, adjusting wind patterns and precipitation accordingly. Everything connects. Warm water here means rain there. Cold currents in one place shift winds halfway round the world. The planet's climate isn't a collection of isolated systems. It's a single, integrated whole, with the ocean and atmosphere constantly exchanging energy and moisture, constantly influencing each other. Now, let's rise higher. Not all weather happens near the ground where we live and breathe. In the upper reaches of the atmosphere, in the thin air 50 or 60 miles above the surface, phenomena occur that most people never see, that were only discovered in recent decades when pilots and astronauts happened to catch glimpses of them. Remember when I mentioned that lightning isn't confined to the lower atmosphere? This is where we explored that idea. Above thunderstorms, in the mesosphere where the air is too thin to breathe, red flashes appear for just milliseconds. They're called sprites, and they look like jellyfish made of light dangling down from the ionosphere. They're massive, sometimes stretching 30 miles vertically, and they happen so quickly that the human eye can barely register them. For a long time, pilots who reported seeing red flashes above storms were dismissed. The phenomenon seemed too brief, too strange. But in the 1990s, high-speed cameras finally captured sprites on film, and the scientific community realized these pilots had been seeing something real all along. Sprites are electrical discharges, like lightning, but they happen in such thin air that they behave differently. The electricity doesn't heat the air as intensely. Instead of the white-hot channel of a normal lightning bolt, sprites glow red and purple from the excited nitrogen molecules in the upper atmosphere. They're ghostly and fleeting, the sky's secret language, visible only to those who are looking at the right place at the right time with the right equipment. Blue jets are similar but different. These are blue cones of light that shoot upward from the tops of thunderstorms, reaching heights of about 30 miles. They're narrower than sprites, more focused, and they also last only a fraction of a second. They seem to be electrical discharges propagating upward into the atmosphere, perhaps triggered by the intense charge separation in the storm cloud below. Scientists are still working out exactly how and why they form. These upper atmospheric phenomena remind us that weather extends far beyond the clouds we see from the ground. The atmosphere has layers, each with its own characteristics, its own forms of behavior. And at the very top, where the atmosphere fades into space, weather isn't driven by temperature and moisture anymore. It's driven by particles from the sun, by solar wind carrying charged particles across 93 million. miles of emptiness to interact with Earth's magnetic field. This is where auroras happen, but we'll drift into that space more gently later, when the night has deepened and we're ready for that kind of quiet wonder. For now, just know that the sky has secrets. Things happen up there that are invisible from the ground, that occur on timescales too fast for the unaided eye, that require special conditions to see. And there's something peaceful in knowing that mystery still exists, that we haven't catalogued everything, that the atmosphere still surprises us. If your attention is wandering, that's fine. Let it wander like clouds drift across the sky. There's no test at the end of this. No need to remember facts or retain information. We're just here, together, exploring the air around us, noticing things about the world that might be new or might be familiar, but seen from a different angle. Your mind might drift to other thoughts, to memories of storms you've experienced, to summer afternoons or winter mornings. That's natural. Weather is connected to memory because it's part of every moment we've lived. You can let those memories rise if they want to. They're part of this journey too. The pace is slowing now. Can you feel it? The rhythm of these words, the space between ideas, everything is stretching out, becoming more relaxed, more gentle. Like the way afternoon stretches toward evening, the way sunlight becomes softer, the way shadows lengthen. We're not rushing toward anything. There's nowhere to get to. We're just here, present with the weather, with the atmosphere, with the endless circulation of air and water and energy that surrounds us always. Ice moves slowly. So slowly you could watch for hours and see nothing change. But it moves, carving valleys, carrying stones, patient and inevitable, like time itself made visible. A glacier begins with snow, not the snow of a single winter, but the accumulated snow of many winters. Decades of snow, centuries of snow, falling and compressing under its own weight. In the high mountains or in the polar regions, where it's cold enough that not all the snow melts during summer, each year adds another layer. The weight of the layers above presses down on the layers below, squeezing out the air, transforming the loose crystals into dense, solid ice. This takes time, decades. The ice at the bottom of a glacier might be hundreds or thousands of years old, formed from snow that fell before anyone alive today was born, before their grandparents were born, before recorded history began in some places. And once the ice becomes thick enough, once it reaches a certain depth and weight, it begins to flow. Ice, which seems so solid, so permanent, behaves like a very slow liquid under pressure. The glacier moves downhill, following the pull of gravity, flowing like a river, but at a pace measured in inches per day or feet per year. You could stand on a glacier and never perceive the movement. But if you marked a point on the surface and came back years later, that point would have traveled. Rocks embedded in the ice would have moved. The entire mass of ice would have crept down, grinding against the bedrock beneath, carving the land into U-shaped valleys, leaving behind scratches and grooves that geologists can read like a record of where the ice has been within a glacier. The ice is not uniform. There are layers of different densities, different colors where dust or volcanic ash was deposited in certain years. There are crevasses, cracks that open where the ice flows over irregularities in the bedrock, where tension pulls the surface apart. Some of these crevasses are narrow, barely a hand's width. Others are vast chasms, deep and blue, their walls glowing with an otherworldly light because the ice absorbs all the wavelengths except blue, which scatters back to your eyes. Inside the glacier, there are sometimes caves, tunnels carved by water, passages of ice that channel water flowing beneath or within the glacier. These ice caves are temporary, formed one season and collapsed or refilled the next, part of the glacier's slow, constant transformation. When glaciers reach the ocean, pieces break off, a process called calving. Huge sections of ice crack away from the front of the glacier and fall into the water, creating icebergs. An iceberg is a piece of a glacier set adrift. And the famous fact about icebergs is that 90% of their mass is hidden beneath the surface. Ice is less dense than water, so it floats, but only barely. The part you see above the waterline is just a fraction of the whole. The bulk of the iceberg extends down into the depths, a massive hidden structure. This is why they're dangerous to ships. What you see from the surface doesn't reveal the true size or shape. The iceberg you're looking at might extend hundreds of feet below, and its underwater contours might reach out far from what you can see. Glaciers are ancient. They're archives of climate, holding information in the layers of ice, in the air bubbles trapped within, in the ratios of isotopes. They're also active, alive in a sense, constantly moving, constantly changing, constantly interacting with the world around them. They feed rivers. They shape landscapes. They're evidence of how much ice the planet can hold when conditions are right. And they're shrinking now, many of them, as the world warms. But the ice itself, the substance of it, has a quality of timelessness. It feels eternal even when it's not. Let that settle for a moment. Slow, ancient, patient, still, Now, let's consider the opposite extreme. Not cold, but dry. Not ice, but desert. The Atacama Desert in Chile is one of the driest places on Earth. In some parts of the Atacama, decades pass without measurable rain. Not just a dry year here and there, but truly decades. There are weather stations that have never recorded precipitation in their entire operational history. The sky forgets to rain. For years, sometimes decades, clouds pass overhead without dropping water. The ground waits. Plants wait. Life waits. Everything waits. And yet life exists there. Not abundantly, not lushly, but it's there. How? Fog. The Atacama is dry, but it's not far from the Pacific Ocean. And when cool ocean air moves over the coastal mountains, fog forms. This fog drifts inland, and though it doesn't rain, moisture condenses on surfaces. Plants have adapted to harvest this fog. Some have leaves or spines designed to catch water droplets from the air. Others have roots that can absorb the tiny amount of dew that forms when the fog touches the cold ground overnight. It's barely any water, just a film of moisture, but it's enough. Life finds a way. In deserts, dew becomes a form of rain. When night falls and the ground cools rapidly, the little moisture in the air condenses on rocks, on plants, on any surface that's cool enough. By morning, before the sun burns it away, there are droplets clinging to everything. Animals lick these droplets. Plants absorb them. The entire ecosystem runs on this marginal moisture. On the thin edge between something and nothing, there's a silence in places that weather barely touches, a stillness. When rain almost never falls, when wind is rare, when the air is so dry that sound travels differently. The landscape takes on a quality of suspended time. The Atacama has areas where the ground looks like Mars, rocky and barren and untouched. Nothing grows. Nothing decays because there's no moisture to support the bacteria that break things down. Objects can sit on the surface for decades, centuries, unchanged. In the Atacama, the sky forgets to rain and time slows to a crawl. But even in the driest desert, weather still exists. Temperature shifts. The air moves. At night, the temperature can drop dramatically because there's no moisture in the air to trap heat. During the day, the sun beats down mercilessly for the same reason. The weather is extreme in its dryness, in its temperature swings, in its absence of clouds. It's weather defined by what's not there rather than what is. And there's something contemplative in that, in recognizing that weather isn't always dramatic, it isn't always visible. Sometimes it's the absence of rain. Sometimes it's the stillness. Fog is a cloud touching the ground. That's all it is. When air cools to the point where it can't hold all its moisture, that moisture condenses into tiny water droplets suspended in the air. And if this happens near the surface, we call it fog. It muffles the sound, softens edges, makes nearby things disappear. Walking through thick fog, you exist in a small sphere of visibility. Everything beyond that sphere ... dissolves into whiteness. There's a disorientation that comes with fog, a sense that the world has contracted to just what's immediately around you. Distances become impossible to judge. Sounds come from unexpected directions or seem to come from nowhere at all. Morning mist in valleys happens because cold air is denser than warm air, so it sinks to the lowest points overnight. Valleys fill with this cool, moist air, and when the sun rises, the temperature difference between the ground and the air creates mist. It hangs there, just above the surface, glowing in the early light. By mid-morning, as the sun warms the air, the mist evaporates, lifting and thinning and finally disappearing entirely. But for those early hours, the valley is transformed. The landscape becomes soft, dreamlike. Half-dash hidden dew forms overnight when surfaces cool below the dew point. The temperature at which air can no longer hold all its moisture. Grass, leaves, car, windshields, anything exposed to the night sky cools through radiation, and moisture from the air condenses on these surfaces. By morning, everything is covered with tiny droplets. They catch the light. They make spiderwebs visible, turning invisible silk into strings of diamonds. By the time the sun has warmed everything, the dew evaporates, returning to the air as vapor, part of the endless cycle of water moving between liquid and gas and back again. Light rain and drizzle are gentle. The drops are small, falling slowly, barely making a sound when they land. This isn't the dramatic weather of thunderstorms or blizzards. This is weather at its quietest. It dampens surfaces. It darkens the color of pavement and wood. It creates a soft, persistent patter, background noise that can be soothing, meditative. You can walk in drizzle without feeling like you're in a storm. It's just there, surrounding you, light and persistent, wetting your face and hair gradually, not soaking you, but slowly making everything damp. There's a particular kind of rain that falls so lightly it's almost not rain at all. More like the air itself is wet. You can feel the moisture on your skin, see it collecting on surfaces, but you never see actual drops falling. It's a mist that might technically be drizzle, or might be something between drizzle and fog. It exists in that borderland where weather categories blur. And there's something peaceful about weather that's hard to define, that doesn't fit neatly into categories. Whether that just ... is now. Think back to something I mentioned earlier, rainbows, and the way they're created by sunlight bending through water droplets. During the day, when the sun is bright, rainbows are vivid. But the moon's light can do the same thing. Under specific conditions, bright moon, rain, or mist in the air, the moon behind you lunar rainbows appear. Moonbows. They're rare because they require a nearly full moon, and they require moisture in the air at just the right angle. They're much fainter than solar rainbows. Often they appear almost colorless to the human eye, just a pale arc of light, because the light from the moon is so much dimmer than sunlight. But cameras with long exposures can capture the colors, revealing that they're there, just too faint for our eyes to see in the darkness. Moonbows are ghostly, quiet. They're the weather's way of whispering instead of shouting. Right now, you're breathing. The planet breathes too, in its way. Air circulates, rises here, sinks there, carries warmth from equator to pole, an endless rhythm, like your breath, in and out, rising, falling, Wind is just air moving from areas of high pressure to areas of low pressure, seeking equilibrium. Warm air rises because it's less dense, creating low pressure at the surface. Cool air sinks, creating high pressure. And between these areas, air flows, trying to balance the difference. That's wind. On a small scale, it's the breeze you feel on a summer day. On a large scale, it's the trade winds, the westerlies, the jet streams. Massive rivers of air flowing across the planet, driven by the uneven heating of Earth's surface by the sun. The equator receives more solar energy than the poles. So warm air rises at the equator and flows toward the poles, while cool air from the poles flows toward the equator. Add in the Earth's rotation, which deflects these flows through something called the Coriolis effect, and you get the global wind patterns that have shaped human history, that determined where sailors could go, that influenced where civilizations developed. The carbon cycle happens in slow motion, but it's happening constantly. Plants take in carbon dioxide from the air during photosynthesis. They use it to build their structures, their leaves and stems and roots. When plants die and decay, or when animals that ate those plants breathe, carbon returns to the atmosphere. Some carbon gets buried in sediments and becomes coal or oil over millions of years. Some dissolves into the ocean. The ocean holds vast amounts of carbon, absorbed from the atmosphere or washed in by rivers. And all of this carbon is cycling, moving from atmosphere to plant to animal to soil to ocean and back to atmosphere, in a dance that's been ongoing for hundreds of millions of years. Weather is part of this cycle. Rain washes carbon compounds from the air and carries them to the ground. Wind erodes rocks that contain carbon. Atmospheric circulation distributes carbon dioxide around the globe, the breath of the planet. And then there's the water cycle, which we've touched on throughout this journey, but which deserves its own moment of contemplation. Water evaporates from oceans, from lakes, from soil, from the surfaces of leaves. It rises into the atmosphere as invisible vapor. It cools as it rises, and when it cools enough, it condenses into clouds. The clouds drift, carried by wind, and eventually the water falls as rain or snow. It runs into streams and rivers, flows back to the ocean, and the cycle begins again. But it's not a simple loop. Water can take many paths. It can soak into the ground and become groundwater, sitting in aquifers for years or decades or centuries before emerging from a spring. It can be taken up by plant roots and released through leaves back into the atmosphere. It can freeze in a glacier for thousands of years. The same water molecule has cycled through this system countless times. The water you drink today has been rain, has been part of a glacier, has been in the ocean, has been inside plants and animals and clouds. It's ancient water and it's renewed water simultaneously. The rhythm of the water cycle is the rhythm of weather. Rain falls, water flows, evaporates, rises, condenses, falls again. It's endless. It's patient. It continues whether we notice or not, whether we're awake or asleep, whether it's day or night. The planet's systems run on cycles like this, slow and steady, not frantic or rushed. There's a comfort in that steadiness, a reminder that some things continue, that some rhythms are larger than any individual moment of worry or stress or sleepless. Your breath is part of this too. You breathe in oxygen that was released by plants. You breathe out carbon dioxide that plants will use. You're connected to the atmosphere not just by being surrounded by it, but by actively participating in these exchanges. Every breath is a small part of the planet's larger circulation. You're not separate from weather, from the atmosphere, from these cycles. You're woven into them. Always have been. Always will be. The air around you is still. Or maybe it's moving gently. Either way, it's there, supporting you, surrounding you. Part of the vast ocean of atmosphere that wraps around the entire planet. And as we move deeper into this journey, as the night deepens and the pace slows even more, remember that you're held within this system, safe, supported, part of something ancient and ongoing. There's nothing you need to do but be here, breathing, noticing, letting the images and ideas settle around you like mist, settling into a valley, slow, patient, endless, still, above you. Miles of air stretch into space, layer upon layer, troposphere, stratosphere, each one filtering light, holding heat, protecting everything below. You're wrapped in this invisible blanket, safe held. The atmosphere isn't empty space. It's substance. It has weight and presence. It presses down on you gently, about 14.5 pounds per square inch at sea level. Though you don't feel it because the pressure inside your body matches the pressure outside. This air surrounds the entire planet, a protective shell that makes life possible. It filters out most of the sun's harmful radiation. It burns up meteors before they reach the ground. It holds warmth close to the surface so that night doesn't become unbearably cold. Without this envelope of air, Earth would be a barren rock, frozen and lifeless, exposed to the harshness of space. The troposphere is the lowest layer, where we live, where weather happens. It extends about 7 miles up at the poles, about 12 miles up at the equator. All the clouds you've ever seen, all the rain that's ever fallen, all the wind you've ever felt, happens in this thin layer. Above that is the stratosphere, where the air is calmer, thinner, where the ozone layer absorbs ultraviolet light. Commercial jets fly in the lower stratosphere to avoid weather. Above that, the mesosphere, where the air is too thin to breathe, where meteors burn up, where those sprites and blue jets we talked about earlier appear. And higher still, the thermosphere, where the air is so thin it barely qualifies as an atmosphere anymore, where the aurora dances, where satellites orbit. Each layer has its own character, its own role. Together, they form a nested set of protective shells. The air at ground level is dense enough to breathe, to support weather, to scatter light and make the sky blue. The air higher up is thinner, but it's still there, still filtering radiation, still part of the system. And at the very top, where the atmosphere fades into space, the air is so sparse that it's measured in individual particles, but even there, it's doing work. Absorbing energy from the solar wind, creating the aurora, marking the boundary between Earth and the cosmos. You're wrapped in this invisible blanket, miles of air above you, all of it working together to create the conditions that allow you to exist. You don't have to think about it. You don't have to do anything. The atmosphere is just there, always, surrounding you, holding you, protecting you. It's been there your entire life. It'll be there tomorrow. It's one of those constants, like gravity, that you can rely on, absolutely. Safe, held, protected, night has fallen. Or perhaps it fell hours ago. Time is becoming less distinct, less important. The world outside your window, if there is a window, is dark. Or maybe there's ambient light from street lamps or the moon. Either way, the day has given way to night, and night has its own weather. Clouds are still moving in the darkness. You can't see them the way you can during the day, but they're there, drifting across the sky. Illuminated faintly by moonlight or city glow, or not illuminated at all. Just invisible masses of water droplets moving through the night air. If the clouds are thin, or if there are gaps between them, stars appear. Points of light so distant that the light you're seeing left those stars years ago, decades ago, centuries ago. The light has been traveling through space all that time, and it's arriving now. Filtering through the atmosphere, reaching your eyes if you happen to look up. The world continues while humans rest. This is a strange thing to contemplate, but also a comforting thing. Weather doesn't stop when you go to sleep. The wind doesn't pause. Rain doesn't wait for morning. Tonight, while you sleep, weather continues. Wind moves across empty fields, bending grass that no one is watching. Clouds form over dark oceans, building and dissipating in the darkness. Rain falls on forests where no one walks, each drop hitting leaves, running down bark, soaking into soil. Snow settles on mountain peaks that are too remote for anyone to visit. Fog fills valleys. Dew forms on surfaces. The entire planet's atmospheric system keeps cycling, keeps moving, keeps working. The world doesn't need you to watch. It continues, peacefully. On its own, there's something deeply restful in that realization. You can let go. You can stop paying attention. The weather doesn't require your awareness. It's not waiting for you. It's not depending on you. It's simply happening the way it's been happening for billions of years, indifferent to whether anyone notices. The clouds will drift across the sky whether you're awake to see them or not. The wind will blow. The temperature will shift. Morning will come, and with it, new weather, new patterns, new movements of air and moisture, and you can rest. You don't need to hear what comes next. It's perfectly fine if you've stopped listening. If your thoughts have become dreams. If you're somewhere between waking and sleep. In that liminal space where you're not quite sure which thoughts are yours and which are part of a dream starting to form. The sky continues. The weather continues. And you can rest. Maybe your eyes have closed. Maybe they're still open but not really seeing anything. Maybe you're aware of your breathing, or maybe you've stopped noticing it. Your body breathing automatically, the way it always does, the way it will continue to do while you sleep. There's no right way to be in this moment. However, you are exactly right. If you're still following these words, that's fine. If you've drifted away and come back, that's fine too. If you're already asleep, then these words are just sounds, just gentle background noise, and they're not reaching your conscious mind anymore. They're settling somewhere deeper, or they're not settling anywhere at all, and that's perfectly fine. The atmosphere above you is settling into its nighttime patterns. The ground is cooling, releasing the heat it absorbed during the day. Air is sinking in some places, rising in others. Pressure systems are shifting imperceptibly. Somewhere on the planet, dawn is breaking. Somewhere else, a storm is building. Somewhere else, the sky is clear and still. All of this happening simultaneously. The planet is turning, the air circulating, water evaporating and condensing and falling and evaporating again. You don't need to track any of this. You don't need to understand it. You can just let it be. Let it happen around you. Let yourself be held within these processes that are so much larger than any single moment. Breathe, clouds, drift, you, drift, all is, well, breathe, the sky is settling, you are, settling, soft, quiet, still, the air around you is the same air that's been here for billions of years. The same molecules, cycling through different forms, but the same substance. You're breathing air that dinosaurs breathed, air that was part of ancient oceans, air that will be here long after you, continuing its endless circulation. You're part of this continuity, part of this cycle, connected to everything that's ever breathed, everything that's ever lived. Rest, the night is deep, weather moves in darkness, you, rest, clouds, drifting, stars, distant, wind, gentle, you, drifting, safe, held, the atmosphere, endless, your breath, slow, in, rising, falling, like weather, like wind, natural, easy, nothing to do, nowhere to be, just, here, just, just, breathing, the world continues, you, rest, soft, still, sleep, sleep, ancient, ice, patient clouds, breath of earth, drifting, resting, the atmosphere wraps around everything, soft, safe, miles of air, above, around, holding, always holding, water, rising, falling, endless cycle, you, part of it, always, part of it, clouds, moving in darkness, you don't need to follow, just, wind, wind, across empty fields, rain, in distant forests, continuing, you, resting, safe, still, slow, in, out, natural, rhythm, like weather, like wind, easy, ancient, ice, remembering, snowflakes, each one unique, drifting down, settling, like Your thoughts settling quiet the sky endless above you held below protected warm safe fog softening edges mist in valleys everything gentle everything soft do forming in darkness moisture condensing the world breathing you breathing together part of the same same air same cycle connected always connected rest clouds drift you drift stars distant light reaching softly through miles of air to here to now you resting the wind continues the rain continues the earth turning the sky holding and you you rest still safe peaceful weather moving in its own time you resting in yours no hurry no need just being just breathing just soft warm held ancient patterns endless cycles water and air rising falling like your breath like your thoughts drifting now into sleep into dreams into rest the atmosphere continues protecting holding and you safe within it always rest sleep quiet peace breathe drift rest safe sleep